Hello everyone. So today we will be looking at this algorithm of sorting. So it is one of the basic algorithms, uh, or rather, which is used in a lot of subroutines. As a subroutine in many other algorithms, and also helps to uh, set up your basics. Uh, so what is sorting? So basically, you have been given a set S and n real numbers. So set S of n real numbers, say a1 to an, and what we are interested in is to sort this set of numbers in an increasing or rather a non-decreasing order, right? So, of course, a natural question to ask is how is this set given? And here we should kind of remember that what all properties that we need for a data structure uh, mm, to access a particular set. So in most of the stuff that we will be doing, we will assume that S is given as an array. So you remember what an array is? So array gives us a random access memory. That means that I can access the ith element. So what is SI? So SI in is accessed in one step, right? But we cannot insert an element or delete an element. So insertion or deletion takes order n steps. Okay, so I mean we will be accessing, we will assuming that this S has been given as an array, but what happens if it is not given as an array? That also we should kind of keep in mind. So to start with, let's start with the simplest sorting algorithm that we can think of. What will it be? The simplest sorting algorithm will be something. Okay, before we go to simplest sorting algorithm, I should say that when we design the sorting algorithm, what are the properties of a sorting algorithm that we need to kind of consider? So, of course, as we have done in the earlier cases, the worst case running time is one of the most important problems or one of the important properties of an algorithm that we would like to keep in mind. But also maybe something like a base case algorithm. Now, what is a base case runtime? Say the input that is given and the set in is already in a sorted order. The array is already in sorted. In that case, how much time the algorithm will take? Now, it is not obvious that the algorithm will always be giving a very nice bound for the best case. Ideally, if you have been given the given an array in a sorted order, the algorithm should not take more than order n number of comparisons or other number of steps. We need order n because uh, the algorithm, any algorithm, has to look at the n elements, right? So without looking at the n elements, how can we expect anything to be done? But it is not obvious that all the algorithms that we have will give us the order n, will take only order n steps even if the input is sorted. The third is of course the average case runtime, and we will come to this property particularly later in the in our next video. Average case runtime is basically if you are given a random ordering of the elements of a particular set, then what is the number of times it is required for the algorithm to output the final sorted order. Okay, so the expected number 9, you can say. There are other things that we have to kind of take into account, like the memory used. See, of course, this to save the S, this uh, mm, save the S, the input S, we need order n steps. But here we say that what are the extra amount of memory that we require? Do we need something much more, or can we handle it without too much more space? Now there are three other properties that are kind of not mm, measuring the kind of speed of an algorithm in some sense. So first of all, called the in-place sorting. What is in-place sorting? Uh, the in-place sorting is that if I have two elements, say so maybe that say I have a huge document, right? I have a huge document and that has a roll number on top, right? And I have another huge document and that have a roll number on top. Now I want to sort this set of uh, documents. So one thing is that maybe I can copy this whole document into a new place. Okay, so I can copy it in some sense, and I say, oh, okay, so my algorithm asks me to copy it, and then I will say that okay, I'll make another copy of this one, and I'll also make another copy of this one, and then do something on that, and something of that form, and then I will do something, but that is not in place. The reason is that because we are copying this whole set for here, it is taking a lot of other space, right? Also, I mean, there are lots of reasons why one would not like to move the whole documents here and there. So instead, if we can do something in which we can do everything without copying into a new area, right? Particularly, maybe we can just swap these two or something like that. Then this is called in-place algorithm sorting. So we will see some examples of in-place sorting and some examples of not in-place sorting, and then you will possibly have a better idea of this. There is also this concept of stable sorting. Okay. So it is basically if you have say so I can remove these things. Say I have 5 parameters, right? So there are the some parameters for a person named B1. I have the parameter P1, parameter P2, parameter P3. So maybe this is the marks in algorithms. 93 is the marks in algorithms, and 91. Sorry, not algorithms. This is the marks in statistics, and this is the marks in so say these are the total marks, say, right? Now I can have this set of students here. P1 to Pn, and all of them have these marks. Now, say I have these two persons, say 90 and 184. Now I have sorted according to this set P2. In that case, what will happen is that this B1, B2 will be ranked higher than B1 or lower than B1, because in this score B1 is highest. Now if I sort now according to P3, it should not be that now B2 goes higher than B1, because already in this given list or given array, B2 and B1 both have the same score for P3. So as such, it doesn't matter which one comes first or which one comes second. But the initial ordering, which is basically B1 is less than B2, that should be preserved. If that is not preserved and some kind of a weird random things happen, so all I care about is that I will just sort it out in terms of P3, and there is no guarantee of what will happen after I what will happen with the initial sorting, then that is not called stable sorting. So stable sorting is something where you preserve the initial ordering. So among the people who have the same number, you preserve the initial ordering. And finally, many times simplicity of a code is a very useful thing to happen. So I mean, if a code is very complicated, then that's possibly not a very good algorithm. So these are all trade-offs in some sense. So there are lots of parameters to judge which algorithm is better and which is slightly worse. And again, we will see, as we will see soon enough, that there are algorithms in which one of the parameters is better than the other, but some other parameters is worse, and so on. So let's go on to the what can be the simplest algorithm that one can imagine. So the simplest algorithm is basically, say I have these numbers, right? I have a number 1, 6, 5, 2, 3, 6, 7, 9, 1. First, one thing we can do is that we will say that, oh, okay, I will go over this whole list, okay, and then find the minimum. So if I find the minimum, say I will, oh, okay, this minimum is this one, and then I write it here. Then I will go over the rest of the list and go and find the next minimum, right? Which is, oh, okay, the next minimum is also this one. Then I'll go and write this. Then I'll go over the whole list all over again and find out the next minimum, and that is 2. And then I'll go over the whole thing again and find out the minimum among rest of them, and then I'll get 3, and so on, right? So this is a very simple algorithm, right? So if I basically give you a numbers to sort, you first find out the minimum among the whole set, you take it out, make it in the first one, take it out, then you look at the rest of the set, find out the minimum, put it on the second one, and so on and so forth. Okay. Now, okay, so this is an algorithm, no doubt about that, right? It is a correct algorithm, and I am not going to prove you the correctness, because you can have a formal correctness proof by yourself. Prove that this algorithm will actually output the correct sorting algorithm, sorted list. Right. Now, what about the runtime? Now, note that to find the minimum of a set, we already know what is the time that is required. It is n minus 1. So, find the first minimum, I need n minus 1 step. Then, so this is just the first. Now, to find the second minimum, I need n minus 2 steps, right? And similarly, so it is actually they are comparisons. We are only going to count the number of comparisons for now. The number of steps might have some more factors here, but let's not worry about it. We are just interested in the number of comparisons that we are doing. So the number of comparisons, therefore, would be something like, I mean, n into n minus 1 by 2 or something, which is order of or theta of n square, right? So n is the, okay, I am not told what n is. So n is the total number, okay? N is the total number of elements there, and even if I forget to tell you at some point, remember that n is always the size of the input, unless otherwise mentioned. N will always mean the size of the input. Okay. So here is an algorithm, a simple algorithm where you find a minimum, you put it in the first place, right? And this algorithm is correct, and it has a runtime of order n square. Now, okay, you remember we discussed about this in place sorting? Is this algorithm in place? Actually, not at least how we have described it. Because we are saying that you first find the first bit, first minimum value, and copy it in a different place. Then you find the second one and then copy it in the same place. So, in some sense, first of all, we are using a lot of more space. We are using an extra order n number of space, and it is also not in place because we are not doing it in place. But actually, this algorithm can be tinkered a little bit to make it in place and without any extra uh, space. So let's see how will we do it. So I will just remove it. Okay. So the way in which we do it is that we start with our two different uh, pointers, right? So one pointer is currently pointing out at the first place, which basically means that we are looking at the first minimum value. Okay, and then there will be another pointer. This part also. Another pointer that is also pointing at the first place. So what we will do is that we will move this pointer along this place and go and find out which one is the minimum, right? And at the end we will bring it back to the place which is minimum, and then we will swap whatever is there in the blue and red thing. So in this case here, say I have found out, oh, the first one is the minimum itself is the first one, and so there is nothing to swap. Okay. Once I am done with that, I will shift both the blue one to the next step and also the next one to the next. The idea is that we are done with this thing, with the first one. Now again we do the same thing. We will move this red one and find the minimum. Here in this case it's the 1. And then what we do is, okay, now we know that the second minimum is the first one and the blue one is pointing at the second index. So in that case we should swap these two objects. Okay, that's the idea. We swap these two objects, then what happens? Note that what I do, I will put the sixth thing over here and I will put the one over here, right? And that's what I have done, and I will remove all possible other things and I move the blue pointer to the next one and also the red pointer to the same place. And now again I will go and find the minimum one. I'll go over the whole set and oh, okay, so this 2 is minimum, and then I will swap these 2, right? So in other words, I will take this 5 and put it over here, and take this not done. Yeah. Okay. So and then again we will remove all these arrows and we move the blue pointer to the next place and the red pointer. So here we are done with, basically you can think of that wherever the blue pointer says is pointing, everything on the left is already sorted and everything on the right is not sorted. And after every round, the red pointer should always point to the minimum value. Blue pointer points to the, just it's a kind of a pointer to wherever we need to put the next minimum, and you swap it. right? So if you do it this way, then note that we are not using any extra memory. In fact, we are completely doing it in place. Okay. The runtime and the proof of k remains almost identical. So here is the pseudocode of this algorithm. So if you see it there, we have this pointer, and okay, I have not written up the rate pointer because this is what rate pointer is kind of hidden in this sentence. It says that find the minimum in the array, so and let the minimum be in the ith place. So that means the rate pointer is pointing at the ith place, and then we will swap the rate pointer and the the value in the rate pointer and the blue pointer, and I move the blue pointer by one step. And at any point of time, we are looking at the array from the blue pointer to the end. Okay. Note that if you have to prove the correctness of this sorting algorithm, this selection sort, since there is a while loop, how will we do it? Recall that the way in which to do it is that we would be trying to give a loop invariant. What will be the loop invariant in this case? So the loop invariant is that the array, okay, it will be that array A1 to APT minus 1 is sorted and contains the smallest PT minus 1 elements. Right. And as you move on, what you will end up having is that you have to prove that in this whole loop, this every round of the loop, this loop invariant is maintained. And once you have this loop invariant maintained, you will be able to prove that the correctness of it. Because when the algorithm stops, which is when PT becomes equal to n, right? In that case, we are basically done. That we will have all the smallest 1 to n minus 1, the smallest n minus 1 elements in the sorted way into A1 to An minus 1, which means that An must contain the largest one, and hence the whole algorithm A or whole array A is sorted. So that is the formal proof of the selection sort algorithm, right? Through the loop invariant this one. Now, so what do we have? So we have this, the worst case running time for this algorithm is n square. Now we have proved that it is at least n, at most n square. You can prove that the worst case is also n square. Why? In fact, it will be kind of theta n square, not just. So all of them will be. Why will it be theta n square? I let you guys go and find out. So how to prove that the minimum thing is worst case is n square? The reason is that you have to produce a particular array, okay, and you have to prove that that is minimum. Note that if I go back, to find the minimum for every step will take nothing less than n minus pt number of steps, right? And that's why it will become n square. So in fact, the best case running time is also n square. So even if the array that has been given to you or the set that is given to you is in the completely sorted order, it will still take order n square. And space complexity, okay, we are not using any extra space. We have just order 1 space because it will, we will call it order 1, but actually it might be something like order log n number of space actually. Why? Because we have to store things like the value of pt, right? And this pt is a number between 1 and n. So I will need an order log n number of steps, but Yeah, it will be order log n number of cells, extra space, and it is an in place sorting. So nice. So everything is nice except for these three parts. These three parts seems to be a bit too much. Can we improve it? Now let's go to the thing. What is the next? What is another algorithm that you can think of? So another algorithm that you can think of is what is sometimes called the bubble sort. So, I have 1, 5, 2, 6, 7, 3, 9, 1. I don't remember what was the initial thing. But is that what I can do is that uh, I will have a arrow, and I will move that arrow slowly, meaning I will actually go over the numbers. Now, as soon as I sum up with a number where this one and the next one is, so basically, as soon as I find a place where wherever it is pointing and the next one are in the wrong order, rather 5 is greater than 2. So, what I can do is that I will try to swap these two objects, right? And that is what I will do. So, what I will do, I will take this 2, okay, I will take this 2 and swap, okay. Then I will keep on moving, by the way. I will keep on moving. Okay, 5 is less than 6, no problem. 6 is less than 7, no problem. 7 is less than 3. Oh no, this is a problem. So I will swap it again. Right? I will swap these two once again. So how do I do it? Oops. Okay. Then I keep on going. 7 is less than 9. 9 is less than 1. Ah, no, this is not true again. So I again need to swap it. Right? So I take 9, put it here, I will take 1, put it here, and I will move this. Ah, good, done. Note that I am not done with the whole thing, right? I have just swapped it. Then I'll go back to the front and go over the whole thing again. 1 is less than 2, 2 is less than 5, 5 is less than 6, oh, 6 is not less than 3. Okay. So I need to swap it again. 3, 6 is less than 7, 7 is less than 1. No, that's not true. 7 is less than 9, 9. Ah, good, very good. Back to the same thing again. So, as you can see, we are progressing, but not as fast. But you can see that we are increasing, right? Now, we are doing something. So, how do you kind of count the number of steps that is required here? How do you prove the correctness of this algorithm? The first thing to prove the correctness is that here is that the stopping time. If the algorithm, as soon as the sorted array, or the array becomes sorted, the algorithm will stop. They will make one round, one pass, and oh, by the way, when does the algorithm stop? If in a particular pass there is no swapping done, in that case the algorithm will stop. Right? So similarly here, the sorting algorithm is that if the array is sorted, then it stops. Okay, after one more round, after one round. So that means the algorithm will stop at the sorted array, it will not keep on continuing. Now you have to convince that, okay, now fine. Now what is the chance that it is going towards the sorted array? So one way to think of it is that look at the actual position of this element, okay, where is the actual positions of this element. For example, say if I use red, so this one should have been in position 1, no problem. This should be in position, actual position 2, right? This should be in position 3. This should be in position 4. This should be in position 5, right? This should be in position 6, this should be in 7, and this should be in position 8. Now note that what you can prove is that the difference between the actual position and its current position. What are the current positions? The current position here is 1, this one is 2, current 3, 4, 5, 6, 7, 8. So the sum of the actual position minus current position, say the absolute value, this will be decreasing, will decrease each round. And this is something that you can prove. I leave it to you to prove it, but you could be able to prove that after every round this quantity will be going down. Now how big can the gap be? What can be the actually the maximum of this value? The maximum of this value can be at most n square, right? So this whole algorithm will of course have a runtime of at most order n square. So in some sense this whole concept will give you both the correctness of the algorithm as well as the runtime. Now you might ask, is this kind of, can you do a better job? I will not prove it to you, but you go and check, verify it, that is actually it is theta. So this I should not write this one. So yeah, the worst case runtime will be theta n square. In other words, there exists a initial input of the array, so that the algorithm will be forced to make order n square number of comparisons. Yeah, you go back and think about it. Okay, what is the worst input that you can think of? So this is what is called the bubble sort, and the pseudocode is kind of given here. And basically what it says is that, okay, so I have a something called a swap, which basically if in one round, if I swap any element, which means that uh, the the array was not sorted, in that case it will be flipped to true, and the whole algorithm will continue for one more round, right? And at any point of time, if the swap has not been turned true, then the algorithm will stop. So meaning that if a round passes when there is not a single swap done, what does it mean? It would mean that the array is actually sorted, right? And then the algorithm will stop after that. And just as I told you, it keeps on going. There is this j that keeps on increasing slowly, and as soon as it finds a uh, aj is bigger than aj plus 1, it swaps it. And the correctness of the algorithm, as we told you that it will be that quantity. Okay. So here the correctness of the algorithm is this loop invariant, is that quantity is going down every time. Okay. So it's not through the, so here is an example where we are not proving the correctness in a loop invariant form. We are proving it in the potential function. So this one is a potential function that we're going to talk about. This is the potential function. And since the potential function is decreasing every round, okay, so we stop. And when, what does it mean by the potential function becomes 0? Potential function, the algorithm will stop only when the potential function is 0, which means that it comes to a state when the actual position is equal to the current position, right? So the correctness of the algorithm is, so correctness using potential function. Okay. So by the way, so let's quickly go over it. Here it is interesting. So the worst case runtime, as we told you, is actually, in fact, this one should actually be theta n square, but the best case runtime is actually theta n. Why? As we told that if the array is already sorted, then the algorithm will not take any more too much time except for one scan. So it's order n only. Now you have to go and prove it for yourself that the average case runtime for this algorithm is also n square. And we have this space complexity, and again this is not O of 1, it should be O of log n, and you have the n class sorting. Okay, so good. So we have made progress. We have increased the best case runtime. Now, many of you are possibly thinking of another algorithm by now. So let's see what is that algorithm. So what this algorithm is that it is kind of a algorithm in which we try to maintain at any point of time a sorted array. So in other words, say I have this kind of a what happens if I do this following thing? I have a measure and I check, oh, okay, the first element, it doesn't matter, it is already sorted. Now I go to, now I move this arrow to the next one and I say, okay, so is this set sorted? Okay, I don't need to check it, right? All I need to do is that I will take this, look at this 2 and go and place it within the sorted array. Okay, in this case, okay, it is already sorted. I find that, oh, sorry, 2 is more than 1, so there is nothing to do. So great. So 2 is sorted. Now I move this arrow to the next one. Okay, and I find that, oh, okay, at this point, is this whole thing sorted? Or in other words, where will I place this 5? Now, how do I place a 5? I of course place a 5 by using a binary search. Note that I am guaranteed that this till now is sorted. So I'll check 5 in the middle and then I'll move and I find out, oh, okay, fine. So 2 is sorted. So I need I need to place this here. So I get something like this. So at this point, I know that everything here is sorted. Okay. Now I move this arrow again. Now I see 3. My goal is to make this whole set sorted, right? But right now it is not sorted. So what I do is that I check 3 with this 2. Okay. Note that I am using binary search to place it there. Okay, and I said, okay, where are you? And then, okay, it should be bigger than 2, so that means it should be here. It is checking for the next one. Is 3 bigger than 5? No, so it should be in between 2 and 5. So what we do is that we now understand where should I place what, right? So I take this 3 I take this 5 and I put it here. Wonderful. Okay. Now I again continue moving here and I find that okay, I do the same thing, right? Is how can I place 7 here? And I do a binary search and figure out that okay, this is also sorted, no problem, excellent. So I go and I understand that 7 is sorted. Similarly, we'll go to 8 and then 9 and you will figure out that everything is sorted. So we will at this point have the whole thing sorted, right? And then we move this arrow to the final one and then okay, how do I place this one so that it's sorted? Now I go and check this to the half of it, middle of it. So is 1 less than 5? Yes, it's less than 5. Okay. Is 1 less than 2? Okay, it is less than 2. Is 1 equal to or less than 1? Okay, it is actually less than 1. So it should be kind of somewhere here. So I should kind of, my idea should be that I should be now putting this 1. So I should put this 1 over here. But how do I do that? There is the tricky part. So that means I need to move this 1 away and then move this whole chunk one step and then move this whole 1 over here. Great. So in other words, I would be maintaining a initial part of the algorithm, the array will always be sorted. When a new element comes, I will do binary search and try to put it there. Now, I think correctness of the algorithm will not be the problem here, right? Because we are maintaining an sorted array and every time we are using binary search to find the place where a particular element should go and I am doing that. So the correctness is basically kind of saying that that the array to the left of arrow is sorted. Now that is fine. But what is the runtime? Okay, you would say that okay, the runtime is at most we will go over all of them. So there are n of them, and in each time we will do a binary search. So the binary search is only at most log of n. So the runtime is log of n and this is n. So total number of steps is order n, log n. This is not true. It is true that the total number of comparisons is order n log n. But see, when I had to place this 1 over here, right, I had to shift the whole thing. So in fact, when I am looking at the ith element, right? So when I am looking at the ith element, this amount of or rather when arrow pointing to index I, right? How much time do I have to spend? I have to first find out the position to place it, which is log of I, and I might be in the worst case have to shift the whole or a big chunk of them, right, of the I things. So it should be I. So the total runtime will become summation over I equals to 1 to n. And this is proof that this is also theta of n square. So although we can use binary search to quickly find the position of an element, but actually to put it there, I need to spend this I number of time, I number of steps. Why do I have to do that? Because the input is an array. In an array, going to an element or doing a binary search is very good, very easy. But to move things, so insertion of an element in that array is very costly, and this is exactly what happens. Now you might say, what happens if I don't use an array? I can use a linked list. In that case, this I will not be there, because I know that in a linked list I can put an element anywhere I want in order 1 steps. But in that case, you cannot do binary search. To find where that element should go, you have to do a scan of the whole set. So this will become I in that case. I if linked list. So in some sense, here is the interesting part. If you have an array, you can save on the finding the position, but you have to spend that much time to insert it. If you have a linked list, you have to spend a lot of time in finding that position, but you save on the insertion. So overall, it kind of, we are not seeing which one is better, right? The array or the linked list. In both of them, it is taking theta n square. So this algorithm is called the insertion sort. In insertion sort, although I have described it in terms of doing a binary search, but see, since there is an I already, however, even if we do an insertion sort binary, if I do a binary search and find that location where the I should be, at the end of the day, in the worst case, I have to spend I number of steps to insert it, right? So instead, what we could have done is basically we could have maybe if I just can use a little bit more thing. Say for example, when we were thinking of moving this when we were thinking of moving this stuff, what we could have done is that we could have kept on swapping this one with the previous one, right? And so 1 and 1 will go to, so say I will be producing 1 over here and 9 over here, then we'll swap 1 with 8 and so on, and still it kind of, you keep on swapping, right? And finally you would be able to produce finally we will keep on swapping 1 by 1, and and at the end it will of course land up in where it should have got, which is 1, right? So basically, once you look at the one element, you swap it till it goes to where it should go. You may say that this is what, we could have done a binary search. Of course, we could have done a binary search, but then again, insertion would have taken that much time, right? So instead, if you don't do binary search and do just this sorting, I don't need this log I factor. I just need I, right? So the total worst case will be summation over I, which will again be theta of n square. So this is exactly what is written up in this pseudocode. I want you guys to go over it and prove the correctness of this pseudocode by yourself. Okay, we have discussed this one. It is exactly what we just now told. Okay, we keep on, once we get one particular element, right, we keep on, when we look at the ith element, we keep on swapping till we can swap, and then we move to the next round. So I is basically the one that is pointing to the place where the arrow is. By the way, in many times in algorithms, we can write the algorithm in multiple ways. So this way of writing it was by the plain simple while loop. But there is another way of writing this particular insertion sort, and that is using the recursive algorithm. What is the idea? The idea is kind of simple, that you take the array and you say that okay, I call, so the recursive algorithm is calling for the A with an n, and it will be outputting the sorted array on the first n elements of A. So I will use the recursive algorithm, I will use the same algorithm with a different parameter and say that okay, go and first sort me the first n minus 1 elements. And once you have sorted the first n minus 1 elements, then all I need to do is I will just do this kind of finding out the position, the right position of an and put it there. Okay, so here is another version of writing the insertion sort. Exactly same thing. In one case we have written up the whole algorithm, in other case we are calling a recursive algorithm. The insertion sort is calling insertion sort itself, but on a smaller input. Okay. This is something very useful. In fact, this is something that is very close to induction. Okay. Or a function, defining a function recursively. In fact, this kind of way of writing a program is called the functional programming technique, in which you write so you write the same, you solve a function by citing the same function on a slightly smaller node. Okay, so I want you guys to go over this algorithm and prove for yourself that this algorithm is also correct. This, whatever is written there, is correct. The correctness of the algorithm is actually exactly similar to the induction algorithm that you can think of. Okay, so where are we? We have this insertion sort. We could not make much progress. We have this worst case runtime of theta n square. Convince yourselves that the best case runtime is theta n, average case runtime is theta n square, and we have a order 1 extra space sorting, and we have an in place sorting, right? So now let's look at another algorithm, the final algorithm in this video, and where we try to get a better worst case runtime. The algorithm is called the merge sort algorithm, and this is actually using the basic technique of what I told you guys of the recursive algorithm. So I have say 1, 3, 7, 9, 5, 2, 1, 8. Say I have said this set of things. So basically what it does is that it first splits it up into two halves. Okay, this is one half, this is one half. So this first half is given to someone else. Okay, and he calls, so this first half, and that person so it goes through another algorithm, and the second one goes to another algorithm, and what comes out is a sorted array. So here it will be 1 3 7 9 as it was already sorted, and it comes to as 1 2 5 8. Okay, so you use the merge sort algorithm on these smaller two sets, right? You have this set on 4 elements and this set on 4. So I have got now two sorted array, right? Now how do I merge them? Now the merging is basically nothing but having two different arrows. There is a two arrow here, and you keep on checking, okay, which of these two things is smaller. And when you say, okay, see, out of them both of them are smaller, so I will just take this one and I place it over here, this one, and I move this one to the next step. Now I compare 1 with 3, and then what do I see? I said, oh, okay, this is smaller. So next one is 1. Actually, I don't need to try and write the rounds kind of stuff. And I will move this one now to the next. Then I say, which one is smaller? Oh, okay, 2 is smaller. So 2 goes, and I write 2. 1, 2. And I move again this 2 to the next. Then I look at which is smaller, 3 or 5. Oh, okay, in this case 3 is 5. So 3 goes here, next. Right? And then I move this one to the next. Then which is smaller, 5 or 7? Okay, of course, 5 is smaller. So 5 goes here, and I move this arrow to the. Then which is smaller, 7 or 8? Okay, it should be 7. Very good. So I move this one to the next one. And now, which is smaller, 8 or 9? Okay, it's 8. So I should write 8. And in that case, this arrow basically now points to an empty space, which is nothing. And I get 9 over here. So I should write 9. So this is the overall evaluation of this whole thing. So we split up the initial array into two parts. Okay, we sorted them recursively, and then we merged them to get the final sorted array. Okay, so there are two parts to it. How to prove the correctness? Now, actually, proving the correctness is actually not two parts, because this part is kind of an inductive thing, right? By induction, we know that whatever we get here and here are sorted. And all we have to do is that prove that in the merging, we have managed to merge it correctly. Right? I will not go over the correctness of this algorithm formally. You guys try to prove it. That merging that I explained, and I will give you the pseudocode soon enough, that it is actually correct. Okay. Now, but the interesting part is, what is runtime? Now, how do you solve this kind of runtime problems? So, first of all, it is solved very recursively. Let's say that Tn is the total time taken to sort this whole algorithm, right? So, what is this Tn? I have used what? I have applied this merge sort on this half this element. So, this must take therefore Tn by 2 in the worst case. This also must take Tn by 2 in the worst case. So, this is 2 times Tn by 2 plus, and now I have sorted them. Once I have got the sorted arrays of the two halves, I have to merge them. Note that in the merging, what happens is that these two arrows, they have moved along these two things. So, it is nothing but the number of steps done is some constant multiple of the number of steps made by the two arrows, which is in total n by 2 plus n by 2 is n. So, in fact, I can write it in order. So, if I erase a lot of some parts of this one, erase some parts of this one. Okay. So, the runtime now becomes T of n equals to 2 times T of n by 2 plus order n. And now use your knowledge of recursion, solving of recursions and all. and prove that that means T of n is theta n log n. Right? This is a very big jump. So we have produced a new algorithm or designed a new algorithm whose runtime or worst case runtime is order n log n, and it is a recursive algorithm. So the pseudocode of this algorithm is basically written here, and you can see here that basically the most important part is this recursive stuff. So we are applying this merge sort on a set A where we are mentioning the low and the high, right? So basically the starting and ending point of the array that we are interested in sorting. And how do I do it? I actually find the midpoint. We find the midpoint, we merge sort these two things, and we then merge these two objects together. Okay, the merging algorithm is written here. I want you guys to go back and think about this merge sort. We will spend a little bit time on something similar. Finally, we have a worst case runtime of order n log n. Now, you prove that this base case runtime is ordered also n log n. The worst case, the average case runtime is order n log n. And but the issue here is that there are two more issues. The space, we are using an extra space because of the merging that we have to do. We are requiring a lot of space. The good news is that this algorithm is highly parallelizable. Okay, it can be broken up into parts, so that means lot of different algorithms can simultaneously, or different machines can simultaneously solve a lot of things. But it is also not in place sorting. So we have this merge sort algorithm, and we leave it here that can we do better? Can we save on the merging? The merging took us order n steps, right? Is it somehow we can do better? Right? Or can we do something more nicer? Right? What is it? What is the correct time complexity for the sorting? And these are the kind of things that we would like to study in the next video.